Well, hey, Calc 2. We're diving back in. We're going to take on volume where we left off, modify things a little bit just to kind of get you the current content, the most important content related to the AP exam, whether you're taking it or not. And that'll just give us a nice focus for the end of the class anyway, just what we've all kind of decided is the important stuff. So now, if you'll find, I sent you guys home with all the volume notes, or you had them when you left. You may have left them at school. But I also uploaded them to Google Classroom. If you're ever missing anything, just let me know. What I'm going to do is everything I write here too, you'll have these videos and I'll send you the PDF document of everything that I write. So maybe it's just a good way to get these organized anyway. Something I've always wanted to do is to put those two things together. So let's play. So we left off with the thing that you did in Calc 1, and it's still ever important in Calc 2. It could be a question on one of these, 4 questions that you're going to get, 45-minute test. On that exam, and the things that I'll still hold you accountable for DMAC. We'll have to figure out how that works out, trying to get, itemize the assignments that meet the necessary standard for you guys to get the credit that probably is going to transfer just fine to all your local institutions. But we did, I think it was the washer method was where we left off. So I'm going to go there, and then I'll do the cross-sectional volumes, but we did a lot of concept stuff. So now I'm going to kind of speed into just using it in a kind of fluid fashion. So if you remember, it's the outer radius squared minus the inner radius squared I'm going to do blue, let's do pink. Pink looks cooler on here. And what it means, if you want to get the volume of a rotational volume around some kind of axis, if you take, for instance, I think we did this example, but it's a great segue into what we've already taken a peek at. So if I do cosine and sine, here's your cosine, and here is your sine. And the region that we're going to rotate about the x-axis forms a solid. And you're going to rotate this fin-like flap. And so when it gets rotated around, what you get is the same shape on the other side. And they kind of carves out this bowl thing. So we did this in class. The volume of that particular solid looks like a cool little, it looks like you could put like an acorn inside here, but it's a bowl that would hold an acorn holder. And the volume of that particular acorn holder is to do this lovely formula. We'll do it, and I'll just use it practically, and then we again talk about what on earth is taking place. These two will meet at pi over 4, so you always have to find those intersections. That ends up being kind of one of the big things in volume, is almost, 9 times out of 10, you're going to need to find the intersection of the two graphs. I know this is sine and cosine. I know where they're equal. And the intersections is where the functions are equal. And so usually it's kind of simple stuff like that. I can't imagine you'd be throwing any curveballs, but set the two functions equal, find the intersections. They're likely going to be necessary. And then when we do the volume of this, you are doing a washer of sorts. You're actually finding the little added together discs, the washers that look like this. They make little rings, consecutive rings. They put them together, and eventually it's going to make the shape of this acorn holder if I just stack them on top of each other. And the carved out inside is what makes the carve in here. It's kind of what's taking place in our particular graph. But we're summing these together, and their width of each of these washers is x dx wide. So ultimately, the volume of this is the outer radius squared. It's getting you the volume of the larger disk, subtracting out the volume of the littler disk, and then taking them each times the thickness of this. And so it's like a little cylinder. And the outer radius is created by that blue, the cosine function. So when you think outer radius, I'm going to go yellow for just a second here so you can see it. Outer radius is from the axis of rotation to the outer edge. And that distance is from the axis of 0 to cosine. You really want to think of it as cosine of x minus 0, which I'm not going to write as minus 0. Quantity squared is the outer radius squared. And then minus, which means carving out the inside. The inner radius squared is the distance from the axis of rotation to the function that creates the inner part of it, which is sine of x. So sine of x minus 0, technically, is that radius distance. But what we're going to do is just get rid of that 0 for now for cleanliness. And voila, this gets you your volume. Now, we're coming up on, should you be taking the exam, it's all free response. So these are the ones you'd have to do by hand. And so what we're going to need is, how about I'll do the algebra on these. I'm going to set them up, and we'll come back in a second video and I'll walk through that algebra, because we're going to have to do the power reduction formula if we were to do this one by hand. And remember, there's a formula to replace those. So I think it'd be a good way to emphasize, all right, I can set it up. That's part of the problem, probably the most important part. But if you need to do this by hand, which is highly likely, here's how you'd use the power reduction formula to anti-derive this, if you can't remember now. Okay, so that's the volume. And by the way, there's a pi out in front. I did forget that part. So it's pi times outer radius squared minus inner radius squared. This would do the job. And I can pull up the calculator and we can get that. But setup is my emphasis at the moment. So down here, I think we got to some of these. And I don't know. I'm going to go to the bottom couple. Maybe finish off this last one here, y equals -5. And see if that kind of rings a bell where we left off. Here are the functions that we were dealing with. I could probably draw them a little bit better than that. There we go. Here's y equals x, and then x squared is going to come out from underneath it. And the region that we're dealing with is what they overlap. And it's that little flap that I've created right there. They intersect at 1, 1, and that's not meant to be a mystery. It really is. When do these two, they equal to each other? X is equal to x squared when x equals 0, and when x equals 1. So we're finding those intersections there. And what we're going to do is the outer radius, and we're going around the x-axis, or in most cases, unless specified otherwise, and it is specified as y equals -5. So I'm going to make that axis way down here. Here's y equals -5, like that. Oh, yeah, we'll call it y equals -5. And when we talk about the outer radius, I'm kind of trying to do that one in yellow, it's from the axis of rotation to the outer edge of the shape when you rotate it. And so if I rotate this thing around, and I'll do it real lightly, maybe in this green color, it looks like this. Here we go. And the inside edge here, this is a horrible likeness, you can make fun of if you like, but it's going to make a kind of a wider, broader dish is the volume that we're creating. And the outer radius is the distance from the axis of rotation to that flat outer edge that you see right there. Okay, so I'm going to go and create that outer radius squared minus inner radius squared times pi, of course, and see if we can make emphasis of that. The region, the bounds that you use over here, what I write for the upper and lower bound, they are going to be x bounds because the washer itself, again, is another washer that kind of orients itself. It's facing up like this. It's dx thick. So the outer radius, and if you want to memorize anything that's around the x-axis or parallel to the x-axis, is going to be a dx integral. So I'm going to put dx at the end, and then the outer radius squared minus the inner radius squared that I'm creating right now. The outer radius is the line y equals x minus the axis of rotation -5. Now, when I subtract those, you get minus a negative, so it's plus 5, and that's where that's coming from. And then the inner radius is created by, I'm going to do red for that one, the distance from the axis of rotation to the curve that creates the inner edge, which is the x squared function. So it's x squared minus a -5, so again plus 5. And that is the setup for getting the volume of that particular shape. And without getting to, and then the x bounds are, what's the lower x bound? 0, to the upper x bound, 1. This will do the job. If I were to integrate this by hand, which would be perfectly reasonable, I'd FOIL both of those out and use the power rule of integration to take care of those. Okay, so that's a fun setup. The y-axis one, so now we're turning it on its side, and I don't know if we got to these in class, and so here's another, here is our region of integration, and when I spin this around the y-axis, then everything changes because what we're creating now this direction like that. Outer edge is curved, the inner edge is straight, and it's a bowl again, but this one would hold something more like a little cone, a little top, a little spindle thing that would sit inside that little bowl. And the outer and inner radius are still distances from the axis of rotation to the outer edge. So inner radius is this red little line there. The outer radius will do yellow again, like that. That's our radius. It's the measure of distance from the axis of rotation to the outer and inner edge, respectively. And so the setup for this one, outer radius squared minus inner radius squared. How much do you want to bet I left off the pi on that last one? It just occurred to me when I went back there. You want to look? Of course I left off the pi on there. I always have to ask myself, did I put the pi in the volume equation? Okay, back here. Let's do it first. pi first. It's like the main course of the meal. The d piece I'm going to leave off. This one ends up being dy, but the reason it's dy is because your discs, or we're talking washers right now, and I only really deal with washers. It's because the thickness of the stacked washers, they create this space. So if I put a bunch of them on top of each other and create the space that you see here, I can do them like this, and do another one like this, like that, and create the space, fill it up, and it has ultimately it would be the same volume that you see above, but with very, very, very thin washers stacked together. Each of them would be, the height of that washer would be measured vertically, so we call it dy. Some people like to memorize with the washer method, if you go around the x-axis or anything parallel to the x-axis, then it's going to be dy, and that's sufficient. You can get by with that. But the outer radius squared minus the inner radius squared. The outer radius is the curved edge is on the outside this time. So here's my outer edge, and it's created by the x squared function. The problem is, as soon as you realize this is a dy, you cannot have x as a rate. Well, you can, but for this volume methodology, you want to have the function in terms of y when you write it in here. So the outer function, which is the y equals x squared function, minus the axis of rotation, which is 0, that's going to be my outer radius squared. The only problem is y equals x squared, you need to solve for x and get this to be plus or minus the square root of y. Just so you know, when you do this function, the right-hand side over here, and I'm going to use purple, this is the positive square root of y side, and on the other side over here, so when I do plus or minus, this would be the negative square root of y side. So the plus or minus kind of matters. It is, there are problems down the road where it matters if it's positive or negative, but those are the two halves of the parabola as it's written in x equals y form. So the outer radius squared is the curvy outer function minus the axis rotation, and we're doing it in terms of y. So I'm going to write positive square root of y minus 0. Don't need the minus 0, but hey, we have room. I'm making emphasis. And the inner radius is the distance to that straight edge back to the axis of rotation. So that edge right there, and that's formed by the function y equals x. Well, we have to solve that for x as well, which is a relatively easy one. Y equals x, you just turn it around, x equals y. So we're just going to put y minus the axis of rotation, which is 0, x equals 0 in particular. So the axis of rotation here is x equals 0. This is our setup. The only last piece that's really, really important that we watch out for is the upper and lower bound. They have to be in terms of y. So as soon as you have a dy function, your functions for the edges, the inner and outer radius edges, have to be in terms of y, and your bounds have to be y bounds. So they have to be in terms of y. So y equals the lower bound, which is 0, and the upper bound of y equals 1 happens to be the same as our x bounds, but conceptually they are different. It's a y value we're writing. Both this setup is perfect, gets you the volume, it works. The simplifying is easier in this one. So if you take a look, you would actually, square the square root of y, so it'd just be y minus y squared, and you can use the power rule to integrate it. All about setup today, no algebra necessary. The next part E, around x equals negative 1, like this, it's the same region we're rotating no matter what. And so we're going around this x equals negative 1, and that changes our radius. So I'm going to mark the radii. That's the key part. Inner radius is that red one. The outer radius I've been doing in yellow, so I'll stick with that. This is this one. To get those measures, these are, again, I'm stacking my washers sideways at this point. So this is going to be dy. And if you begin memorizing it, this is an axis, that's parallel to the vertical axis. And so when it's around the y-axis or something parallel to the y-axis, it's dy in terms of washers. So we put the pi out front. The outer radius is the yellow piece, which would be the square root of y minus the axis of rotation, which is negative 1. We'll make it plus 1 in a minute, quantity squared. So let's go back to the other one. I think I got everything written in carefully, but things that I tend to forget are the squared or the pi. Those are easy things for me to forget. So just keep an eye out for them. Let me know if I miss them. And then minus the inner radius squared. And the inner radius squared is that red chunk. It's the y equals x function minus the axis of rotation, but we're going to use y, the y form of it, minus a negative 1. And the y bounds again are 0 to 1. That's y equals 0 to y equals 1. And just a little bit of simplifying will take us a long way on this one. That'd be the square root of y plus 1. Quantity squared minus y plus 1 quantity squared. Could all be distributed out, done by hand if we had to. We'd have to know the power rule for that. Okay, so the last one, x equals 17, just gives us one more point of emphasis. Running a little bit low on room because I kind of delved into the territory there. I wonder, what if I did f down below? So if you don't mind, I'm going to take f down into this region. Okay, so it's around x equals 17. Put a line up there. Here is 17, like that. Da-da-da-da. Same region that we're integrating. And when we rotate it around x equals 17, it still makes kind of a bowl shape. Outer edges straight, inner edges curved. It's a funny looking kind of dog dish. Of course, there's a hole in the bottom and the top. But we're rotating this same shaded region from 0 to 1. And we're rotating around the vertical line, x equals 17. The outer radius, now this is where it gets funny to measure the radius. It's from the axis of rotation to the outer edge. The inner radius is from the axis of rotation to the inner edge. I'm going to keep my color coding the same. So yellow for outside. Okay. And the distance for the outer radius squared is axis of rotation minus the outer edge. Now, maybe when I've been doing the function minus the axis of rotation so far, but if you remember back in the old days, it's helpful to do the right hand function minus the left hand function, or between the axis of rotation and the edges of the rotational region, you want to make sure you do right minus left or top minus bottom. And on the right, in this case, x equals 17 is to the right of the region being rotated. So we're going to do 17 minus, and since we're doing the dy version of this because it's something parallel to the y-axis, then you need to make sure they're y bounds. I got pi in here. It's still y equals 0 to y equals 1. The region I'm rotating, the bounds of the integral are always for the region you're rotating, not for what results. It's not the resultant figure. But 17 minus the outer edge, that yellow, is created by the line. So I'm going to put down y. Instead of y equals x, I'll choose x equals y. And the inner radius is the curved square root function, square root of y. But you don't want to put square root of y minus 17. That would be left minus right. You want to put the 17 minus the square root of y, right minus left. And I didn't leave myself enough room, didn't I? Let's space this a little bit better. There we go. 17 minus the square root of y gives you that inner radius location. And so this time, let's go back and look at that. The inner radius is in red. The outer radius is in yellow in each case. So if you go back and look at the other ones I've done, I've kept the coding kind of the same way. The outer radius is measured yellow, and the inner radius is in red. Outer radius, inner radius. That's the hardest part, is making sure that you're taking the axis of rotation minus the edge, outer edge or inner edge, and you do right minus left. So sometimes it's the axis minus the edge or the edge minus the axis, whichever is to the right starts that subtraction, or which one other one is vertically above. You start with that in your subtraction. It actually, some of these, it doesn't make a difference. The consequence of not doing it in the right order can be your region has a negative result. There's a little bit of protection going on in these because they're squared in this formula, but it's good practice. Do the right minus left, top minus bottom, and prepare for the moments when it is consequential to have it in the right order. So down below, we're going to get into, so you did washer. That gives you a good summary of the washer method and when you need it. It's stacking washers to fill a region. If you go into this one, here's the bundt cake problem. The washer method falls short. It's not possible. So we introduced something called the shell method. So you got to use the shell method in this one, because if I don't, I'm going to try it without it. I'm going to use my same color coding. If I'm going to rotate around x equals -1, according to my last, this is the region, by the way. I'm going to highlight it in blue. It's this kind of upside down parabola. It shows you over here. It's 3x minus x squared is the function. And if I carefully shade that a little bit better, if I do my regular old washer method, the distance to the outer edge right there looks like it's, to the function y equals, and we're going around the y-axis. So if we wanted to, we could solve, here's y equals 3x minus x squared, just making sure I'm writing the right thing. Because we're doing washers that would be on their side, you would need to make sure these are dy washers. So you'd have to solve for x, and solving for x in this actually involves quadratic formula is one of the ways you could do it. So you'd have to do x equals the opposite of b, and you could do this, okay? So you can get a function. Gotcha. So you'd get this function of y on this side, and it can be done, and by the way, quadratic formula would do it, so no big deal. But the problem is, when you go and measure the inner radius, it involves the same function. So the inner radius is created by the same exact function. So think about what that would look like. You would end up doing an integral where your outer radius would be the axis of rotation and the function being subtracted, the function's on the right. So you'd have this f of y minus negative 1, so it'd be plus 1, quantity squared, minus the same f of y creates the inner radius, plus 1 minus a negative 1. Let's create that squared and dy. And then be integrating, your y bounds would be 0 to the peak of that parabola, which looks like it's 2. And so that'd be 0 to 2. And you won't forget your pi, because there it is. But the problem with this, using that method, you would end up with 0. And we all know the volume of this thing is not 0, because this is the same thing squared minus the same thing squared. You get 0. So the method doesn't work unless you were to split this into two chunks. And so you can use the washer method on this one only if you do two pieces. You actually break it up into two chunks, because then you have a consistent outer edge and an inner edge. So to do the washer method, you'd have to break this in half. So how about this? The things that I want to fill in later are, one, the algebra that goes with doing some of these by hand, and two, I can show you how to do this with washer method. I'll make that part of that video too. It's kind of like the details of this unit. Right now I'm going with the concepts and the setup of the integral method, but then I'll come back later and I'll give you guys the details on how to do it by hand, and by the way, do this one with washer method if you would choose to do so. But the moral of the story on this one is that would be a lot of work, and there's another method that's a lot quicker, and so we call that's the shell method. I'm going to go and call it, let's do purple. The shell method is, instead of using stacking washers, which these kind of look like washers almost the way it's drawn in here, but instead of doing washers stacked on top of each other, we're going to do cylindrical shells, as in like a shotgun shell. So it's a different kind of shell than maybe you're accustomed to thinking of. It's not your, so here's my top of this. It's just a bunch of tubes together. So here's one. I'll show you guys a picture of this too here in a minute, because it's a pretty good, I'm just stacking this on the outside, and you just make shells, concentric shells on the outside of each other. Okay, so they just line up like this, and you can fill in a space with kind of concentric shells or tubes embedded inside each other. In fact, one of the things that would work really well is if you had, think of it as like a toilet paper roll. So if you think of, here's your, imagine that, this is, wow, is that timely or what? It's like the world of all the toilet paper jokes that are going on right now, but here's your toilet paper roll. Think of it as this could be shaved into the form of this bundt cake that you see right here. So if I took a giant toilet paper roll, let's see if I can put it on top of here, like that. Effectively, so here's my center of my toilet paper roll. I could carve it down to this shape underneath here if I just shaved off the outer edges of it. Okay, so let's get this to something like that, this region right there. And after you rotate it around, you could carve off, but you'd have to take off all this outer edge stuff. So let's get my pink going here. You'd have to take off and shave off all this, and think of like taking kind of like a, I don't know, some kind of cool buzzing device, saw device, and you could carve off all this extra toilet paper, and what would be left behind is this bundt shape. And the cool thing is you all know that that's, since it's made of toilet paper, let me take some of that shading off of there so you can see a little bit better. Okay, so getting back to where we all started, you could leave behind this bundt shape, and it would still have the slices of toilet paper inside there. In fact, basically this would still be rolls of toilet paper. You could unravel this. You could cut off a piece of this and unravel it, into strips of toilet paper. They would just be really weirdly shaped strips of toilet paper. They all be a little bit different heights because you cut into this, you took away a lot of the contents of it, but it would still be pieces of toilet paper wrapped around some inner ring. The tube on the inside would still be there, albeit a little bit carved down to a smaller size, and then you'd have the paper around the outside. So the shell method is actually the sum of all those toilet paper pieces that are left. They're just added up, the leftover toilet paper pieces, because they're still in the form of a ring wrapped around an inner center. So we call it the shell method because this cake, you can think of it as being the sum of a bunch of toilet paper pieces wrapped around that same inner tube. It just happened to be shaved down to the shape of this kind of bundt cake. So probably a terrible analogy, but if I get this thing shaved down, I'll show you a picture in the next video. I'm going to pull up some things that explain the shell method, but I'm going to stop here and say this is just your prep for that, and say this is the final chunk of the washer method, and now your time is to practice it. Next is how do I do all these by hand, and then after that the shell method, which is necessary, or I think a really healthy tool in a situation like this bundt cake, where if I had done washer method I'd have to break it into 2 regions and add it up. So ta-da, round 1 down. I'm going to make this a little bit smaller. See you at the next video.